In this video, we briefly introduced the series RLC circuit, capacitive reactance, inductive reactance, impedance, and resonance. So this is the series RLC circuit with a sinusoidal voltage of sine omega t applied across it. And I see my resistor, inductor, and capacitor in series. Now just a reminder about the way I've written this with an omega in front of t. You could express this in terms of period by remembering that period is 2 pi divided by the coefficient of little t in the sinusoidal function, so 2 pi over omega. And that means that frequency, which is the reciprocal of period, can be written as omega over 2 pi. And then we could write that omega is equal to 2 pi times the frequency in hertz. Now the idea of the reactance of a capacitor or an inductor is that inductors and capacitors have some effective resistance in a circuit in the sense that they resist the flow of current, but this isn't the same as the resistance of a resistor that dissipates power. So it has to have a different name. So you can think of reactance as effective resistance for one of these circuit elements. Then to motivate the formula for capacitive reactance, in other words, the effective resistance of a capacitor, we think about how a capacitor behaves with really high frequency versus really low frequency signals. If you imagine a really low frequency sinusoidal signal across this circuit, for example, like 1 hertz, 1 oscillation per second, then for such long time periods, it's very easy for the capacitor to get completely charged up and block the flow of current in the circuit completely. In other words, in the low frequency limit, the effective resistance of a capacitor is infinite. For very high frequencies, the capacitor would barely charge at all, and you could barely tell it's there in the circuit. In other words, capacitors are sort of transparent to the highest frequency signals. So we can quantify this with a formula for capacitive reactance. And what I want is a very high reactance if the frequency is low, and a very low reactance if the frequency is high. And the way the formula turns out is like this. We use the Greek letter chi for this. The capacitive reactance is just 1 over omega c. In terms of frequency, I could write it as 1 over 2 pi f c. Now with very high frequencies, I get very low reactance and vice versa, so it's doing what it's supposed to do. I do want to look at the units of capacitive reactance real quick. Frequency has units of hertz or 1 over seconds, so I end up with seconds in the numerator. And then capacitance is charge per volt, coulombs per volt, so I end up with coulombs in the denominator and volts in the numerator. Then I see seconds per coulomb. Well, that's the reciprocal of coulombs per second, which is current. So this must be equal to volts over amps. And then using Ohm's law, I can express volts with V equals IR as units of amps times ohms. And the amps cancel out, and I get ohms for my units of reactance. So again, this is a measure of effective resistance in the circuit. It's just that it's frequency dependent, unlike a resistor. What about inductive reactance? Well, using the same sort of physical reasoning about high and low frequencies. We know that inductors resist changes in current. So when you change the current through an inductor, that creates flux through the coil, and there's an induced EMF opposing that flux change. The bigger the inductance, the more intense the induced EMF. So if we were to run a really low frequency signal over an inductor, it's going to offer very little effective resistance because the flux just isn't changing that fast. So inductors give you really small resistance when the frequency is low. If the frequency was really high, then you're just constantly reversing the direction of the current very rapidly, and you get huge induced EMFs opposing those changes in the inductor. And the effective resistance of an inductor can become infinite in the high frequency limit as you're trying to shift the current back and forth infinitely fast. So the simplest way to get this done is with the formula chi L equals omega L. Replacing omega with 2 pi f, I get 2 pi f L. Again, it's instructive to look at the units here. So the units of chi L. For frequency, that's 1 over seconds. For inductance, that's henries. So I have henries per second. And then I have to think about where the self-inductance was first defined in order to figure out a more useful way of expressing the henries. And I'll post a link to the video where this was done. But just as a quick reminder, we have that the induced voltage as a magnitude anyway would be L times the rate of change in the current. L is measured in henries, the induced EMF measured in volts, and the current, of course, is amps. And so I'm going to solve for L in terms of all these other quantities, and I would get volts times seconds divided by amps for a Henry. So a Henry is a volt second per amp. Our factors of seconds are going to cancel. And again, I have volts per amp, which I already showed gives me units of ohms. So again, my inductive reactance has units of resistance on it. This is an effective resistance in the circuit. Now the total effective resistance in an RLC circuit is called the impedance of the circuit, and Ohm's law will still apply. So our impedance, it gets the symbol Z instead of R because it's not exactly a resistance. And I can say that the peak current in the circuit will be equal to the peak voltage over Z, the total impedance, or just depending on the context, maybe I want an RMS current instead, and it would just be VRMS over Z. And the point of this video is not to get into the weeds of how we derive these things, but our total impedance is given by this formula, where R is the resistance of the resistor, chi L is the inductive reactance, chi C is the capacitive reactance, and they combine in this very non-simple way in order to create a total effective resistance or impedance for the circuit. Now something really interesting happens if you look at this formula and think about, well, when is the total impedance minimized? And it's minimized when this chi L minus chi C term is 0. And those are both frequency dependent quantities. So what we can do is look for a frequency that minimizes the impedance. Remember, the effective resistance of capacitors and inductors depends on the frequency. So what we're going to do is try to find the special frequency giving us the lowest resistance in the circuit. That will give us the highest peak current or RMS current if we want to evaluate it that way. And this is called the resonant frequency for the circuit. So we're searching for resonant frequency. And we just say, okay, let's let the inductive reactance equal the capacitive reactance. Express those in terms of frequency, and then solve for the frequency. So I'm going to multiply both sides by 2 pi f, which gives me a 2 pi f quantity squared on the left, 2 pi f quantity squared. At the same time, I'm going to divide by L, and I get 1 over LC. I take the square root, and I get 2 pi f is 1 over the square root of LC. And finally, we divide by 2 pi. And we get an expression for the resonant frequency of our circuit. 1 over 2 pi root LC. So for an RLC circuit, we can imagine sweeping through frequencies from low to high for our signal generator. And that's what we have a picture of in the lower right-hand corner. I'm looking at the peak current as a function of applied frequency. And you'll see that peak current grow and grow and grow to some maximum value. That's right when you hit the resonant frequency, you get the maximum peak current. And then it starts to drop as you go to a frequency that's too high. So there's this one frequency that sort of perfectly balances the effective resistance of the capacitor and the inductor to minimize the impedance and give you maximum current. The farther you get away from that special frequency, the lower the peak current becomes. So let's wrap things up with an RLC example. I'm given an RLC circuit with a resistance of 3.5 ohms, a capacitance of 2 microfarads, and an inductance of 0.1 millihenries. And I'm told the circuit is driven by a sinusoidal power source with an RMS voltage of 2.0 volts. Part A, give me the resonant frequency for the circuit. So we're just plugging into that little formula. Resonant frequency is 1 over 2 pi root LC. Changing my millihenries to henries, I have 0.0001 henries for the inductance. And then my capacitance was 2 times 10 to the negative 6 farads. And I get 11,254 out of this, so I should round it somewhere. And I'll go ahead and express this in kilohertz. So I'm going to call it 11.3 kilohertz. So that's the frequency where you will see the maximum current response in the circuit. In part B, I want to get the peak current corresponding to this resonant frequency. So the way we're going to do that, again, is by using Ohm's law, except using the impedance for the total effective resistance. And the peak current would be the peak voltage over my impedance, which again is a frequency-dependent quantity. So to begin with, I think I need to get the peak voltage. I was given the RMS value, and the peak value is just square root 2 times that. And this gives me 2.83 volts. Then I write down the formula for the total impedance. And then it's not as much work as it seems here, because the whole premise of how we get the resonant frequency is we found the special frequency for which the inductive reactance and capacitive reactance were equal. In other words, that piece of the impedance vanishes, and all we have is the square root of R squared, or just the ordinary resistance in the circuit. So my total impedance has to come out to 3.5 ohms. So then I just apply Ohm's law. I is V over R, and I have 2.83 volts for the peak voltage over 3.5 ohms for the total impedance, and I've got 0.809 amps for the peak current in the circuit. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.